In example 3, we've got the velocity of a car defined by this function here, which is called a piecewise function. So for any value of t between 0 and 4, the acceleration is given by 4t minus 0.5t squared, and then for any value of t larger than 4, it's given by another function. And so when we're working with these kind of functions, we need to make sure we use the appropriate function for the time that we're working out. So in part A, we're asked to find the acceleration of the car after 5 seconds. So a time of 5 seconds tells us we need to be using the bottom function here. So let's work out the acceleration then. So to find acceleration, we do the derivative of velocity. As we're doing it at t equals 5, we use the bottom equation. So when t is greater than 4, the acceleration is given by dv by dt, which is 0.8t minus 6.4. And then we can say at t equals 5, a equals 0.8 times 5 minus 6.4, which gives us minus 2.4 meters per second squared. In part B, we need to find the car's displacement from the starting point when t equals 3 and also when t equals 10. Now t equals 3 is relatively straightforward because we can completely ignore the second part of the function and just work with the first part of the function. So for t equals 3, the change in displacement between 0 and 3 is given by the integral between 0 and 3 of 4t minus 0.5t squared. We can just pop that into our calculator. And that gives us 13.5 meters. Part 2 is a little bit more complex. Here we're trying to find the displacement at t equals 10. What we can't do is just integrate between 0 and 10 because the second part of the function here, when t is greater than 4, is only valid for values of t greater than 4, so we can't use t equals 0 in that equation. So what we're going to do is we're going to end up doing two separate calculations. Before we go about answering part 2, I'd just like to sketch these on a graphical calculator. I think it might help us to understand the problem better. So we're going to draw both functions, but we're not just going to type them in like this, we're also going to specify the domains as well. So I'm going to use x instead of t, so I'll have 4x minus 0.5x squared. But if I just leave it like this, it'll draw the graph for whatever region fits on my screen, and I want to restrict it to 0 and 4. So I'm going to put a comma in. Then I'm going to open a square bracket using shift and the plus key. And then I'm going to specify the domain using interval notation. So I'm going to put a 0, followed by a comma, followed by a 4, and then close that bracket using shift minus. So that's the first one set up. If I just press draw now though, it's highly likely the scale won't be what I want. So first of all, I'm going to go into view window by pressing shift and then V window. At the moment this is set up for trig graphs, so I'm going to change my scale. If I just press standard, it will automatically set the axis from minus 10 to 10. So that might be a good starting point because I'm going from 0 to 4 and then a bit more than 4 later. So let's see what that looks like. As you can see, the graph stops at t equals 4. Let's go back and input the other function. And for the domain this time, we don't have an upper limit. So what we'll do is just put a big number in. So I put a comma, open another square bracket, put 4, and then comma 99. Now this is not strictly speaking interval notation now because we wouldn't have a square bracket here, we'd have a curve, but it won't work on our calculator. So we're just going to use square brackets whenever we need to do this. So I've put 99 and I could put any upper limit I want there essentially. And then if I draw that, we can see this graph only starts at t equals 4. And this is the shape of the path that it will follow. Notice that up here, we have a point at t equals 4 where both curves give the same value. So we've got a graph looking more or less like we want, but we can now maybe tidy up the scale so that we can see all the parts of the graph that we want. So we'll go back into view window. As I'm interested in the value of t at 10, it makes sense to make my x value just go slightly past that. So I'll put that in as 11. And as there are no negative x values, -1 might be a good value there. That just gives me one either side so that the graph doesn't go right to the edges. For the y values, there aren't any negative ones there, so maybe -1 would be there. And as we saw before, the max value didn't really go off the screen, so we can leave the max y value as 10. That gives us a nice graph of the curve now. So we're finding the displacement at t equals 10. So what we're going to do is we're going to integrate using the first function between 0 and 4. That would give us the area of this bit. And then we're going to integrate between 4 and 10 separately. That will give us the area under here. And the total displacement will be the sum of those two areas. So we'll start by calculating the first displacement, which we'll call x1. We need to integrate between 0 and 4 for the first function. As we've already done this calculation, we can just modify the limits on our previous calculation. That gives us 64/3. We'll call the second region x2, and we need to integrate between 4 and 10 with the second function. For that part, we get 96/5. So, at t equals 10, the displacement is 64/3 plus 96/5, which gives us 40.5 if we round to 3 significant figures. Right, so now it's your turn to have a go at problem then. In problem 3, part A is quite similar to the question I've just gone over in example 3, but part B is a little bit more challenging. So have a go at it first. If you get stuck when you get to part B, come back to the video, and I've got a hint that I'll reveal in a few seconds. You might want to look at that first before you look at the solution. It might give you just enough information to have a go at it. Okay, pause the video then. Okay, here's the hint for part B. So in part A, you'll find the displacement at t equals 2. You need that for part B as well. And you're also going to need to do another integral where one of the limits is an unknown. That means you'll have to do the integral by hand because you can't use your calculator to do it. So in part 1, to find the displacement when t equals 2, we want to be using the first function. So we're going to get x equals the integral between 0 and 2 of 14t minus 5t squared. Let's put that into our calculator. And we get 44/3 or 14.7 to 3 significant figures. Notice that I've written down both the exact value and a rounded answer. The reason for that is that for the next question, I'm going to need the answer to this calculation, so an exact value makes sense. But also, whenever I'm giving an answer to a question, I should round it to a certain degree of accuracy. In part 2, we need to find the displacement at t equals 5, which means we need to use both functions. First of all, we know that from t equals 0 to t equals 2, change in displacement, we'll call it x1 in this case, is going to be 44/3. Before we go ahead and do the next calculation, I just want to spend a bit more time practicing drawing these on the graphical calculator. So we'll do it a bit quicker this time. The first function, we've got 14x minus 5x squared. Restricting the domain, we want comma, open square bracket, 0, 2, close square bracket. And then for the second one, 13 minus 20 over t squared, comma, open square bracket, 2, comma, and then a large number. And we'll set our view window up again. So here's the scale we had last time. We went from -1 to 11. This time we only need to go as far as 5. So let's set the max as 6. Don't yet know what this will look like on the y-axis, so we'll have a quick look. Seems like it goes off the screen, so maybe we need to go a bit higher than 10. Let's say maybe go up to 15. And that seems to fit on a bit better. So we're finding the displacement at t equals 5, that's over here. So we're doing the integral of the first one. We've already got the answer to that part, and that's 44 over 3, plus the integral of the second part will get us this area here. So we're going to do the integral of the second function between 2 and 5. That gives us 33 metres. So the total displacement equals 44 over 3 plus 33, which gives us 47.7 to 3 significant figures. Okay, so in part B then, we're trying to find out what is the time when the displacement is 35 metres. Well, we know in the first 2 seconds, we travel 44 over 3 metres. So I'll call that displacement x1. And just to get a picture of that, that is about 14.7, roughly. But we'll use the exact value for our calculation. So we still need to travel quite a bit further in order to get to where we need to go. But what we can do now that we know this is we can write down an equation that represents the displacement at 35 metres. We can say that first of all, in the first 2 seconds we travel 44 over 3 metres. And then the rest of the displacement is covered by the integral of this second function. And the limits for this will start at t equals 2. We don't know how long it's going to take us to get there though, so we need to have a letter here. I'm going to use capital T. But we know if we add these two displacements together, we want to arrive at the answer 35 metres. From here, it's just a case of simplifying things and then doing the integration. So if we subtract 44 thirds from both sides, 35 take 44 thirds gives me 61 thirds. And we can simplify this integral before we do it. We can write 20 over t squared as 20 t to the minus 2. And now we can just do this integral. We can't use a calculator to do it this time. 13 integrates to 13t. If we increase the power, we get t to the minus 1. Divide by the new power, that will cancel this minus sign out and make it a plus. We'd end up with 20t to the minus 1. But I'm just going to write that as 20 over t. Now we'll substitute in our limits. We'll substitute in capital T first. That gives us 13 big T plus 20 over big T. Substituting in the lower limit gives us 13 times 2 plus 20 over 2. Let's simplify everything down. We don't need these brackets at the beginning anymore. Inside this bracket here, we've got 26 plus 10 is 36, but we're subtracting that, so we've got minus 36. Adding 36 to both sides gives us 13t plus 20 over t equals 169 over 3. From here, we've got a hidden quadratic. You can see it more easily if you multiply both sides by t. That would give us 13t squared plus 20 equals 169 over 3 times t. Making one side 0, we get a quadratic we can solve in our calculator. So we go into the equation solver, polynomial degree 2, and if we solve that, we get 3.94 and 0.390. However, only one of these answers makes sense because to solve this, we had to use the integral where t is bigger than 2. So we know that the time we're looking for has to be bigger than 2, because after 2 seconds we've only travelled 14.7 meters. So we can say, since we know that t is bigger than 2, t equals 3.94 seconds to 3 significant figures.